There we go.
Great. Well, welcome everyone. Thank you so much for joining us today. We have a really unique opportunity to hear from some NASA scientists in our heliophysics workshop series. So today is the first one. And we are so lucky to be joined by Nat to hear about what they are working on in the realm of heliophysics. So typically in our StarNet webinars, we're offering professional development, showcasing hands-on activities for you to do in your library programs. But today it's really just a treat. It's an opportunity for you to learn, be a participant yourself. And hopefully you can take some of this knowledge back with you in any heliophysics programs you might be doing in your library. But it's really just an opportunity to hear about some really cool science and what's going on with our sun. Brooks, do you have anything you want to add before we turn it over to our guest presenter?
No, I don't. I just we've been talking about solar eclipses. If you've gone to some of our webinars and worked with us over the past few years, and solar eclipses are great, but I think every time I hear about solar eclipses, I want to know more about the sun because it is kind of crazy and fascinating. So, Nat, I think is going to tell us all about the sun. And I think this just kind of goes well with like some of the stuff we've been talking about over the past few years. Nat has some excellent illustrations and comics. I don't want to spoil anything too. So yeah, I just hope everybody enjoys it. Should be a good time.
Great, thank you. So I'm gonna share my screen because it has this in it. There we go. Okay, hopefully people can see that well. So yeah, I'm Nat Mathews. Thank you so much. I'm so excited to talk to you guys. And I'm going to talk about coronal magnetism, mass ejections, and space weather prediction, and not in that order. So I'm a scientist at NASA Goddard in Maryland. I'm going to talk a little bit about me and how I got there, but I mainly want to talk to you about cool science. So space weather, why do we care about space weather? Where does it come from? How we predict it right now, and how we want to get better at predicting it in the future. So first of all, a bit about me. I am from Massachusetts originally, Western Massachusetts, and I was not always a science person. I used to be a performing arts person, but I looked through a lot of telescopes from a lot of very kind, very patient amateur astronomers in Western Massachusetts, where the skies are very dark. And then I went to school in upstate New York, where I did some simulations of black holes, black hole neutron star collisions. There's this big thing called LIGO, which is a huge hallway we shoot lasers down, and the laser measures the length of the hallway really precisely. And we use that to detect gravity waves that are spun off from black hole collisions in distant galaxies. And we did simulations of that, basically. And then I moved to Colorado, where the Rocky Mountains start. So the Great Plains just sort of all turn vertical all at once. And I did some rock climbing out there. And I started working on sun math because a ton of people study the sun in Colorado. And then I moved to Maryland to work for NASA and do more sun studying. So what is space weather? Why do we care about it? So the solar wind is a bunch of plasma blowing off of the sun all the time. It's all around us in our solar system. It's buffeting the Earth and other planets, things we put in space. There's all this plasma, hot charged particles blowing off the sun, protons, electrons. And the sun is spinning. And as the sun spins and it's blowing off all this stuff, it creates this spiral. We call it the Parker spiral. So this picture right here is the solar system. And all these little dots are planets and the sun's at the center. And we have this plasma spinning off of it. And this is a simulation I'm going to run. So we can see this, the sun is spinning, the plasma is spinning around it. And then this big thing erupts out of the center and plows through all the plasma. That's a coronal mass ejection. It's a big hot ball of more denser plasma than the ambient solar wind, and it pushes through everything and leaves this wake. There's this shock front where it goes. So we want to be able to predict that, basically, because it affects us. Here's us living on the Earth. I've drawn this picture of the Earth. I'm a math person, by the way. I'm not traditionally a physicist, and math people like to draw on chalkboards a lot. So I have some chalkboard diagrams in this talk because I couldn't bring my chalkboard around to every library. So I hope that's okay. But I've drawn this picture of us living on the Earth. And here's the nice ambient solar wind. It's squeezing our magnetic field a little bit. So the magnetic field near the sun has been compressed, and the magnetic field on the opposite side of the sun has been sort of squeezed down as the solar wind is blowing over us, like we're a rock in a river. But when a coronal mass ejection comes through, like one did just like a month ago now, it creates these beautiful auroras, because there's a lot more charged particles coming into our magnetic field. And it looks very nice. Another big one happened in Mother's Day. But there's also, we put a lot of satellites in space too, right? And not all of these satellites are as protected by our magnetic field as we are. So when a coronal mass ejection comes through, if it hits a satellite, it can be bad. The satellite does not like that very much. So we want to be able to predict this. That's really why we talk about space weather. Or at least when I'm asking for funding, that's why I say I'm talking about space weather. Really, I just think it's neat, but in practice, it matters for stuff like this. And it really does matter. So this is a plot of those protons and electrons, that solar wind in space near the Earth. So we measure these protons and electrons and how fast they're going near the Earth. And this is a plot of that from 2021. And basically all these gray bars right here and here and here are shocks. There, you can see the speed of all these particles shooting up because this coronal mass ejections are coming at us. So here's a big shock, here's a big shock, here's a big shock, and right in the middle of all of this, Starlink launches 40 satellites into space. At this red line right here, Starlink launched a bunch of satellites into space for orbit, and it lost all of them. The company lost all of them because the atmosphere was denser than they expected, and it was poor launch conditions because of the plasma interacting with our upper atmosphere. So it would have been really nice if someone could have told them, hey, maybe don't launch 40 satellites. We're in the middle of a big solar storm. Nobody did that, but it would have been nice if someone had. And so we want to be able to do this. We want to be able to predict this better. Here's a schematic of the ISS. And there are these big blocks. Yeah, would they have listened? That's a good question. Maybe now they will. Maybe next time they will. There are these big blocks on the ISS. They're about this big, and they're radiation shielding. And the crew quarters and the command quarters of the ISS are carpeted. The walls are covered with these shielding cubes to protect astronauts from solar radiation during storms. And so we want to be able to protect our astronauts during crewed missions. We want to be able to say, go to a safe place. There's a storm happening, and we want to be able to tell them you're safe for a while. There's no storm happening. You can come out and do science. And so better understanding of when the space weather is happening is really helpful. And for going to the moon, again, or Mars eventually with more crewed missions, we want to be able to do this more precisely and protect people in space. So where does space weather come from? Well, it comes from the sun, right? Mostly comes from the sun. These are pictures that we took of the sun with a camera called SDO that I'm going to talk more about in a little bit. It stands for Solar Dynamic Observatory. And also SOHO, which is a different telescope that looks at the sun. This is from Mother's Day this past year when we got those coronal mass ejections that gave us some auroras, not the auroras we had this past fall. It's a very exciting time to be the sun. But the sun has a magnetic field too, like the Earth's that I showed earlier, but it's a lot more chaotic. It has these bands of magnetic field, these structures, active regions that twist and break. And when they break, they release a bunch of plasma into space. And I'll talk more about the details of that later. Here's another picture. I really like this one. This is older, but you can see the sun is shooting off a bunch of coronal mass ejections, and one of them hits the camera right there. There are these different plasma boiling off the sun, and one of them actually hits the telescope, and we can see the charged particles interacting with the CCD camera. So we want to be able to tell in advance when that's going to happen. What is an active region? What are these bands of magnetic field? So basically, the sun has a big belt inside of it of magnetism that is pushing out in some places. So it has this girdle of magnetic field inside of it, beneath the surface, banding near the equator. And every so often it pokes out. And when it pokes out of the surface, it makes an arch of magnetism, which I like to sort of abstract and think about as like the kind of arch you get on a on a U magnet. So I pretend we have this U magnet right under the sun that's generated by this inner dynamo. And it has this arch of magnetic field connecting the two poles of the magnet. So we have this bipolar magnetic field, but it doesn't usually look exactly like this. It's usually a little bit twisted. So it's twisted like this. And we can't see it. Remember, we can't see magnetic field lines directly. All you have to do is pull a fridge magnet off and look on the back side of it. There's nothing, you don't see little lines connecting it to the refrigerator, right? But what we can see is the plasma filling these magnetic channels, like water in a riverbed. We can't see the riverbed, but we can see the water. So being able to look at the plasma and know things about the magnetic field is hard. But it's all we can do. It's all we can try to do. So we have this magnetic arch, and it twists and twists, and it builds up energy. Like if you've ever taken two ends of a slinky and you twist the two ends of the slinky, it binds up tighter and tighter and tighter, and eventually it pops, right? And when it pops, you get this island of plasma and closed magnetic loop, and that release of energy shoots it into space. That's a coronal mass ejection. That's the thing we just were looking at videos of. How can we forecast that? How do we know if that's going to happen? Well, what we do now is we watch and we wait for a CME to happen. That's sort of the best we can do right now. When a coronal mass ejection occurs, we catch it on camera and we draw these little wireframes. They're pretty faint here, but you can see these little green wireframes around the coronal mass ejection. And we try to figure out what the shape of it is and how fast it's going by looking at a few pictures. And these are actually screenshots from the utility that the actual observers here at NASA use, the operations people who are doing space weather prediction. They fit what they tell me they call an ice cream cone, but it's like a conic shape of plasma density. There's no magnetic field information in it because we don't have that information, but they fit it to the coronal mass ejection as best they can by eye. And they pass those parameters into a computer simulation like the one that I showed originally, right? The plowing through the solar wind. And we use those computer simulations to predict how long it will take the CME to get here. You can go and look at this. So you can actually go to NOAA's website and look at the space weather enthusiast dashboard, which is basically actual measurements of predicted and present fluxes of protons and electrons and how fast things are going, what the magnetic fields are and stuff like that. It's really useful when the aurora was happening recently. But I think it's so cool that you can actually just go and look at this. We live in space, and you can do measurements of space, and we can look at them, we can predict them, and share them with the community. It's a community effort. So how well do we do? I've talked a lot about predicting space weather. How does that go? How are we doing with it? It turns out not awesome. Most coronal mass ejections take about 3 days to arrive, but quick ones can get to us from the sun in less than a day, and really slow ones can take like a week or more. But on average, it's about 3 days. And if you observe a CME on the sun and you say, this is when it's going to get to here, you're going to be a little bit off, right? How off are you? It turns out most of the time we're about a day off. So we're saying the coronal mass ejection will hit us in about a day, in 3 days, plus or minus a day. Is not great. And for ones that take a long time, we're really off. Oftentimes, if we say it's going to take us 5 days to get to us, we're off by like 2 to 3 days. So that's not great. It makes it very difficult to predict and forecast and work on those forecasts. Airlines don't like it when you say, hey, there might be a big coronal mass ejection that will impact your flight paths in 3 days plus or minus 2 days. They're not a big fan of that. And on the bottom chart here, I've plotted every coronal mass. Well, I didn't plot it. My friend CK plotted it. But it's a plot of every coronal mass ejection of the last decade and every prediction that was made of how long it would take that coronal mass ejection to arrive. That a few different people predict these things. And what you would really like to see is a nice triangle, right? We used to be bad at it a decade ago, but we've gotten better and better. The error bars are getting tighter. We're less and less off, and we're better at predicting them now than we used to be. That's not what this plot looks like. It's pretty constant. We were off by about 1 to 2 days a decade ago, and we're still off by 1 to 2 days now. By the way, you can see the solar cycle in this plot because the sun is more and less active in 11-year cycles. And you can see that like 5 or 6 years ago, there were not nearly as many CMEs as there are now, or there were in 2014. So that's cool. But we're not getting better at this. Why are we not getting better at this? We have better computers now than we used to have. We have better models now than we used to have. We look at the sun a lot more than we used to. I think a big issue lies in that initial condition, the ice cream cone that we're using. Because we don't know anything about the magnetic field when we're doing it. We have no idea what the magnetic field structure in this coronal mass ejection is, and that matters when it plows through the solar wind. And we also can't predict these things until they erupt, right? We're not looking at these active regions, these U magnet arches, and saying that will erupt tomorrow. We're waiting until after the coronal mass ejection happens. And then we're saying, we're looking at how fast it's going and trying to extrapolate from that. And third of all, we just have one view, right? We have this plane of sky view. It's projected, right? I have no idea, just looking at this static picture, if that CME is angled away from me or towards me, or directly off into space tangent to me. I have no idea. It's hard to know. You can kind of do some stuff with like Doppler shift, because light that's coming at you is a little bit bluer, and light from things going away from you is a little bit redder. But that's tricky. So how can we do better? Why do we have these problems? Why don't we know anything about the magnetic field in these CMEs? Well, it turns out it's hard to study the sun. It's pretty close, and it's really big. And it's been there all my life, and all your life, and longer than that. So you'd hope that we knew more about it, but it turns out it's hard to study the sun. I would like to take a magnetometer, right, or like a compass, into these active regions and measure the magnetic fields there, but we can't because the magnetometer will melt. So we have to do something else. We did send Parker Solar Probe close, it touched the sun, But when we say touched the sun, we really mean it grazed sort of the upper corona. It's not going to get close to the sun where these active regions actually live until end of life, when we throw it into the sun. So that's not a long-term solution either. But we can measure things without going inside of them. We do it all the time when you go to the hospital, right? If you get like a CT scan, you get into this big machine that measures you sort of from every angle and uses that to diagnose what's happening inside of you, right? So can we build one of these machines around the sun? I pitched this to NASA. They did not like it. It turns out it takes as much mass as several entire planets to build one of these. So we're not going to do that. We could break it up and build a bunch of telescopes, satellites orbiting the sun, carpeting it, sort of getting every angle. And we might do this in the future. We're talking about it, but there are some logistical issues. Like, it's hard to talk to a satellite on the opposite side of the sun than we are because the sun's in the way. It's hard to send a radio signal through the sun. It's very big and very bright and very dense, and you can't do that. So you have to talk around it. It's tricky. And also, it's also expensive. And it's logistically difficult. It takes a long time. We're not even sure how we could do this exactly, but we're talking about it. But for now, we're much more limited. We basically just have this view, right, from home, where all of our best satellite telescopes are orbiting the Earth, and all of our best ground-based satellites are on the ground on the Earth. So this is pretty much the view that we have. So we have to make do with this. How can we make do with this? Perspective can fool us, right? We don't see the magnetic field. We just see the plasma. And so this plane of sky issue of where like all of our observations are degenerate along the line of sight, right? It's hard to know how twisted things are, how tilted they are. And that can make it difficult to really diagnose the magnetic fields in these active regions. Well, we're not going to stop. We're not going to quit. We want to do this, and we're not going to give up, right? Just because it's hard. So how can we push science? How are we studying right now to try and do some cutting edge things to get better at this in the future? So the pictures I showed before of those dashboards are like how we're doing it right now. When you go to the NOAA dashboard, what people are actually doing to give you those CME predictions. Now we're going to talk about what I do as a scientist to try and get better at this. So here are some real pictures. They're the only real pictures in the whole talk. That's the Solar Dynamic Observatory, the satellite I was talking about before that was taking those pictures of the sun. Here are some more pictures of the sun that it took. It measures the magnetic field on the sun, on the surface of the sun, the part that's opaque. And we use those measurements to create a simulation on a computer of magnetic fields that could hook up to those magnetic fields on the surface. So volumetric fields that could connect to those surface fields. And then we synthesize observations of those things and we compare them. So I'm going to talk about that in more detail. But first, like I said, I'm a math person, not a physics person. So I'm already getting uncomfortable looking at these real pictures. I hope you enjoyed them. We're going to go back to abstractions. There we go. I'm much more comfortable now. There's my drawing of the Solar Dynamic Observatory and surface magnetic fields on the sun and models of magnetic fields that we can run on computers or U-magnets and observations that we can take. So I said polarimetric on this slide. What is that? What is polarimetry? So when light goes through a magnetic field, I said we couldn't see magnetic fields, but we actually kind of can. When light goes through a magnetic field, it polarizes, which basically means that all the light waves reorient so that they're all waving the same way. They become less chaotic and they sort of orient relative to each other. And you can detect polarization. You can have these gratings that only let through light that's sort of waving at one angle. This is how 3D movies work now. They used to have like red-blue filters, right? But now they use different gratings and they show the left and right eye images at the movie theater in different polarizations of light. If you've ever taken like nice polarized sunglasses and tried to look at a phone through them, you'll notice you can see your phone oriented some ways, but not other ways. It's the same thing happening. Your phone light is polarized. Light that goes through a magnetic field is polarized. This is not a perfect way to detect magnetic fields because because it's degenerate. Magnetic fields that are at different angles can polarize light the same way. But it's something. It gives us something. So here's the plan. Here's the idea. We take observations, both from the surface and other kinds of coronal observations, atmospheric observations, and we run them through a big computer simulation. Here's my drawing of a computer model. And we produce a possible volumetric magnetic field model of like a kind of thing the sun could be doing. And then is that the sun is doing is the question, because different magnetic fields could hook up to this surface picture. Well, we will create synthesized polarimetry. We figure out what this model would look like if you looked at it through polarized light. Here I've drawn what we call a lagomorph because it looks like a bunny, looks like a rabbit. So basically magnetic fields that are angled different ways at 90 degrees to each other can both polarize the same way. So you have this two-eared signature where the polarimetry is sensitive to magnetic fields that are like 45 or 135 degrees, and they detect that basically. This is rough, right? The twists will have small signatures in here. And different kinds of polarization are sensitive to different angles. So we can use all of this data and compare the synthetic polarized image that we have, this lagomorph we drew with a computer, to the real lagomorph picture from the sun. And they won't match, but we can use the way they don't match to tweak our model and try it again and do that over and over and over until they match better. That's the idea. Here's a science paper diagram that we published with this idea, where we had this ensemble of a bunch of computer models. And for each of them, we generated a bunch of kinds of polarized light images. Here's another example of a kind of signature that you get from looking at magnetic fields with polarized light. And then we quantify how poorly they match the real one. And then we find the model that matches the best. So what have we learned? What have we talked about? We have space weather that comes from the sun, right? And it impacts everything. It impacts satellites, it impacts telecommunications, it impacts people. There was this huge solar storm in the 19th century called the Carrington event, wherein a coronal mass ejection so powerful hit the Earth that telegraph operators reported being able to send and receive telegraphs when their telegraph wasn't plugged into anything. If that happened today, it would not be great for the internet. So we want to know if that's going to happen. And we can predict these. We want to do a better job of predicting them, right? Science is all about pushing forward our understanding. And doing better at space weather prediction will probably take having a better idea of what the sun is doing right now. And we're working on that. We're working on figuring out how to combine observations that we take of the sun all the time, like I showed at the very beginning, right? The SDO and like the solar storms from Mother's Day, taking pictures like that and combining them with computer models to get better measurements of these active regions, these loops of magnetic field on the sun that can twist and break and make coronal mass ejections. But that's still very preliminary science. We're still working on it. And right now we're working on doing it with machine learning, which I can talk about after if you guys have questions about how we're pushing forward with that. Yeah, I have a lot of people to thank who have helped me with the science or with talking about the science. Karina Allman is one of the people at our prediction center at NASA. Anna has helped a lot with this stuff, this outreach stuff. Okay, Barbara Thompson and Sarah Gibson and Kevin Delmas and Tom Berger are all scientists who do this science stuff with me. Yeah, that's it. I'm gonna look at the chat now, but yeah, if you guys want to talk about this, I would love to talk about this with you.
Great. Thank you so much, Nat. Just wonderful presentation. I mentioned in the chat, I wish that my math and science textbooks in high school were illustrated by you, because I think I would have understood the concepts a lot better. But yeah, we can open it up to questions. And participants, you do have mic and video capabilities. So if you want to unmute yourself to ask a question, you are welcome to do so.
I used to teach college calculus. I used to teach math, and I have a lot of thoughts about how we teach math in our culture. Mm-hmm. That's not about this, but I do, yeah.
Nat, I know you didn't necessarily study like space science in your undergrad or anything like that, but so what specifically drew you to the sun? I know you said, you know, there was a lot of heliophysicists and sun scientists in Boulder, but was there anything in particular that
so
you?
there are two basic kinds of science questions. There's what we call a forward model, which is like if you have a rock and you know how heavy it is and you know how strong gravity is and you let go, how long will it take to hit the ground? That kind of like forward, modeling something forward in time, or from boundary information, can you model, you know, what's happening outside of the boundary? Those are forward questions. And then there are inverse questions, which are like, if you have human tissue and you can only measure it from the outside, like its elasticity, how squishy it is, if you can pull it, is there a tumor that's hard inside? Can you answer that from just these sort of degenerate external observations? People who are dowsing for water, for deep well drilling, do the same thing. They send seismic waves into the earth and they try to figure out where discontinuities in the crust are with sound waves, right? So they're doing these indirect observations. And the sun is full of those. Every question about the sun basically is one of these inverse problems. They're called inverse problems, by the way, because they're backward. It's if you know how heavy a rock is and you know how long it took to fall, can you tell me how strong gravity is? And if gravity is constant, that's an easy question. But if there's like a black hole in the middle that the rock fell past, it becomes a lot trickier. So I think those kinds of questions are really neat. And I also was really interested in space. I was doing like black hole simulations, and I was really interested in studying stars. And we have a star that's more accessible than any other. It's a great laboratory to do stellar physics with. It's a lot more accessible. We can look at it half the time. But we can like study it. We have good resolution of it. We can look at it from different angles. We can see the spin of it. And so I really wanted to study the sun as sort of a Rosetta Stone for stars.
Because as you were telling me yesterday, our sun is a pretty good lab specimen to figure out more about other suns.
Yeah, it's in many ways an average star, and in some ways it's an above average star. So it's really neat to study. It's a little bit more magnetically active than most other like stars of its class. We have a biased sample, right? Does that matter? Maybe. Have you noticed anything on Earth, any patterns that naturally occurs along with coronal mass ejections? Do birds act weird? Do insects go quiet? I've had the great opportunity of going to total eclipses a couple of times. And if you have not had the opportunity to do that yet, and you find yourself with one in the future, I cannot recommend traveling to totality highly enough. It's not always the most accessible, but if you can, absolutely do that, because that does happen. Animals freak out, everything gets still. It's like sunset in every direction. Coronal mass ejections are not so noticeable most of the time because they often don't make it to the ground. We have this incredible shield that is bulwarking us from dangerous radiation in the form of our magnetic field. Mars doesn't have much of a magnetic field anymore. It just has some that's sort of imprinted in the rocks. But the actual dynamo inside of the planet to generate that magnetic field is gone. And it's lost basically all of its atmosphere now. There's just a thin shell of it left because it's been scoured away by the solar wind and by coronal mass ejections. We still have a magnetic field that's protecting us. So most stuff from the CME doesn't hit us. So it's not really noticeable to animals. It does impact our magnetic field when a CME comes. It peels away some of the outer layers and flips them around to reconnect on the other side. And that's actually how half the aurora happens. But the aurora is really the main thing that you can see and notice with your eyeballs when a CME happens. I do wonder if birds notice. That's a study I would love to see. I feel like birds might notice, but I don't, because of magnetic directionality. But I don't actually know if that's true.
Yeah, and Tina, that's a great question. Our presenter tomorrow, Dr. Christian Ferradas, he is going to be talking a little bit more about the magnetosphere. And he does have a slide actually that indicates that some animals that use the Earth's magnetic field to navigate can be impacted by coronal mass ejection. So he'll speak a little bit more about that tomorrow. But
yeah, the studies already exist and you can learn about them. You should do that. Yeah. One of the things you have to learn to cope with as a scientist is that you want to know all the science, and it turns out there's too much science to know all of.
Great. Any other questions? Awesome. Well, again, huge thank you to Nat for sharing your work and giving us this presentation. As I said, this is the first of a series of presentations on heliophysics. The next one is tomorrow at, I think it's 10 a.m. Mountain Time. So you all probably already have the registration link if you joined today, but I'm going to put it in the chat one more time in case you want to share it with any colleagues that might be available to join our talk tomorrow by Dr. Christian Ferradas. And we will be putting this recording on our StarNet YouTube channel, so you can access it later, or again, share it with patrons, share it with your colleagues. Also, the slides that Nat used to present, we will include that with the recording. So if you want to use any part of those slides for any programs you're doing around heliophysics or solar science, you're welcome, and you have Nat's permission to use those slides. All right. And yes, with that, I think we are going to end the presentation. So thank you all so much for joining. Thank you, Nat. Thank you, Anna, for coordinating this with us. And hopefully we'll see some of you tomorrow at 10 o'clock.